last time we talked about zero input response for a series RLC circuit. And we begin this lecture with zero state response for a parallel RLC circuit. Now let's talk about step response for the following circuit. Find step response for the inductor current. This is what we call a parallel RLC circuit. We have current source here. And our three components, a capacitor, resistor, and inductor, are connected in parallel. This is IS, C, R, and L. This is capacitor voltage VC. And this current is what we're after, inductor current, IR. So since we're dealing with step response, by definition, it's zero state response. That is, the initial conditions of the dynamic components are zero. That is, initial inductor current is zero, and initial capacitor voltage is zero. And also, again by definition, what we apply from the input of the circuit is a unit step function. Okay, so by definition, IST is U of t. Okay, this is unit step input, and again by definition, IL 0 minus 0 and VC 0 minus V0. Okay, so zero initial conditions. Okay, so what we do is we're going to obtain the differential equation describing the evolution of the inductor current, and then we have the initial conditions, and we will be able to solve it. So let's therefore work out the differential equation. What we do is we start from KCL, which says that the current provided by the input must equal the sum of these three currents, IC, IR, and IL. IC plus IR plus IL. Now what we want is, because this is what we're after, we want to express everything in terms of IL and its derivatives. So let's do that. So that equals, by the terminal equation of capacitor, we have CD, VC, okay? And since everything is parallel, VC is automatically VL. So we can write that for CDVL for IC. Plus IR. IR is VR over R, and VR is VL. And so for IR, we can write VL over R. And finally, we let IL be as it is. And then we use the terminal equation for the inductor, which says VL equals L VIL. Okay, so what we have is CD L DIL plus 1 over R L DIL plus IL must equal IS. Okay. Therefore, we have reached our goal. We obtain an equation only in terms of IL and its derivatives, and also the input. Therefore, what we can do is, let's rewrite the last equation that we obtained. We can write P squared IL plus 1 over RC DIL plus 1 over LC IL equals 1 over LC times the input. Okay, so that's the differential equation for parallel RLC circuit. If we didn't have any input in the circuit, then the differential equation would simply be this thing equals 0. Okay. Now, this is our differential equation. What else? We need the initial conditions. Now, the initial conditions for this differential equation means we require IL at 0 and DIL, the rate of change of inductor current at the initial time. So IL 0 minus equals, by definition, 0. And also we have DIL 0 minus. Okay, so somehow we have to express this in terms of the initial conditions of our dynamic components, namely IL 0 and VC 0. Now DIL 0 is VL 0 over L, using the terminal equation of the inductor, and that equals, for the parallel RLC circuit, VC 0 over L. Okay. And since VC 0 is also 0 because we're dealing with the zero state response, so everything is 0. So these are the initial conditions. Okay. Now we're ready to start talking about the solution. For that, let's pick some values for our circuit parameters, RLC, and then obtain the step response for the inductor current. Example. Let R equals 1 ohm, C equals 1 F, and L equals 1 Henry. Okay? So remember that we're working with the parallel RLC circuit. C, R, L. This is IL. And this is VC. Okay. So for T positive, because IS is the step function, okay, so we can replace this with U of T. For T positive, this is just a constant input, okay, at one end. So therefore, for T positive, we have T squared IL plus DIL plus IL equals 1. Okay, because U of T is constant at 1 for positive times. And this equation directly came from this general expression by plugging in R, L, and C values equal to 1. Okay, so this is the differential equation, and we want to solve that, but this is the differential equation for T positive. Okay, therefore we need the initial conditions for this differential equation, namely IL and DIL at T equals 0 plus. Okay. Now let's therefore talk very little about IL 0 plus and DIL 0 plus, DIL 0 plus. And then we would have the differential equation. We will have the initial conditions for T positive. We have the differential equation, and then we can talk about the solution. Now, what's IL 0 plus? Or can IL, the inductor current, experience a jump at T equals 0? So we have to look at the circuit to determine that. In order for the inductor current to experience a jump, okay, it must have an impulsive voltage. Okay, its voltage must have some impulsive character at that point where we expect a jump. Now, its voltage, the inductor voltage, is the capacitor voltage because everything is parallel, and capacitor voltage, by assumption, is always, at least for the circuits that we consider, is always bounded. Okay, since capacitor voltage is always bounded, inductor voltage is always bounded. Therefore, in this circuit, capacitor inductor current must always remain continuous. It cannot experience any jumps. Therefore, IL0 plus value must equal IL0 minus. Okay. So therefore, we have 0 for IL0 plus. How about the IL0 plus? Now, the IL0 plus is VC0 plus over L. So let's check whether the capacitor voltage can experience any jumps. Okay. Now, in this circuit, in order for the capacitor voltage to experience a jump, it must have an impulsive current, okay, at that particular time. So let's see whether the capacitor can have an impulsive current for this configuration. Inductor current is bounded, okay, by assumption. And then how about the current of the resistor? Resistor voltage is capacitor voltage. Capacitor voltage is bounded, therefore resistor current is also bounded. Okay, so IR bounded, IR bounded, and this is the input which also is bounded, even though it's discontinuous. Therefore, by KCL, whatever the capacitor current is, it must also be bounded. So that means, for this case, the capacitor voltage cannot experience any jumps either. Okay? So, VC0 plus equals VC0 minus. So therefore, VIL0 plus must equal 0. So, the differential equation is here, initial conditions are here, so we can now talk about the solution. So what we do is, we look at the differential equation, we look at the left-hand side of the characteristic. From that, we extract the characteristic polynomial, and then we figure out its roots, and those roots tell us the structure of the homogeneous solution, okay? The form of the homogeneous solution. So, now we obtain homogeneous solution in that way, and this time we have an answer right-hand side, so that means we also have to deal with the particular solution. For that, we look at the form of the input, form of the right-hand side. It's constant, therefore the particular solution should also be constant. So we take our candidate particular solution, plug it into the differential equation, and that directly tells us what the particular solution is. So what we do is we put the particular solution, we sum it with homogeneous solution, we obtain the overall solution, and to that overall solution, we apply the initial condition constraints. Okay? And that will give us the unknowns in our homogeneous part of the solution. And with those unknowns computed, we will have obtained the step response for ILT. Okay, so let's do that. For this differential equation tells us that the characteristic polynomial for this circuit is s squared plus s plus 1. And this can be written as s plus 1/2 plus 3/4 square plus 3/4. And this tells us where the roots are. The roots are at, the roots are a complex conjugate pair with real parts at -1/2 and imaginary parts at plus minus square root of 3/4. Okay. So those roots we call the natural frequencies of the circuit. S1, 2 are the roots of the characteristic polynomial, which are at -1/2 plus minus j square root of 3/2. Okay. So when we have complex poles like that, the response is called underdamped. Okay. And qualitatively speaking, underdamped response displays oscillations, but those oscillations are not sustaining oscillations. They are decaying as time goes on. Okay, so now we can write the homogeneous solution, or the form of the homogeneous solution. Okay. Homogeneous solution. IHT equals, we have K1 e to d. You look at the real part, okay, that gives us the exponent of the exponential part. E to the minus 1/2 times t, and then that's multiplied by a sine with frequency square root of 3 over 2 radians per second. Sine square root of 3 over 2 t. Okay. And also we have a cosine term, and that has a separate unknown k2 e to the minus t over 2 cosine square root of 3 over 2 t. So that's the general form of homogeneous solution. What else? We have the particle solution. Okay. Just like in the first order case, we look at the right hand side. Right hand side is constant, therefore the particle solution has to be constant. I pt equals a. So let's call that constant a. Okay. And how we find that constant is we take our candidate, put it into differential equation, and it immediately tells us what that constant should be. So let's do that. D squared ip plus dip plus ip equals 1. For ip equals constant. Okay. Now, since ip is constant, its derivative is 0. Its double derivative is also 0. So what we have is that constant equals 1. So immediately we see that the particle solution has to be 1. Okay. Therefore, the response, the step response, should look like K1 e to the minus t over 2 sine square root of 3 over 2 t plus K2 e to the minus t over 2 cosine square root of 3 over 2 t. Okay, homogeneous solution plus particle solution, which we computed to be 1. Okay, now to this complete solution, we apply the initial condition constraints. Okay, so that means 2 constraints, which is nice because we have 2 unknowns, meaning that we require 2 equations. So let's do that. Initial condition constraints, we have IL0 equals 0, plug in t equals 0, the sine term disappears, and what we have is k2 plus 1 equals 0. Therefore, k2 has to be minus 1. K2 equals minus 1. Now differentiate this solution and then plug in t equals 0 and equate that to 0. That will give us the second equation that we require. DIL0 equals 0 implies 2k1 minus 1l k2 equals 0. Okay. And k2 was already known, therefore k1 has to be minus 1 over square root of 3. Now everything is determined. We're therefore ready to write the solution. Therefore, ILT equals minus 1 over square root of 3 e to the minus t over 2 sine square root of 3 over 2 t, okay, plus minus 1 e to the minus t over 2 cosine square root of 3 over 2t, and finally plus the particle solution, constant 1. Okay, that's 4t positive. Okay, now what happens is this is constants. so therefore it will remain there forever. And as for these guys, these sine and cosine, they oscillate, but those oscillations are attenuated by this function e to the minus t over 2. So as time goes on, these become smaller and smaller, and in the limit, this part completely disappears, and what we're left with 1. Since, therefore, this first part, or homogeneous part, has some contribution or a significant contribution for the beginning of time, but for later on, it becomes more and more insignificant. This part is called transient now. Okay. And what remains after the time goes on is called steady state part. Okay, since it's constant, it's DC steady state. So what it looks like is IL A T 0. So we start from 0, okay, with 0 slope. Okay, we start with a flat manner, and eventually what we're going to do is we're heading toward 1. But how we converge to 1 is by making certain oscillations. So the curve will look more or less like this. Okay. So to make some oscillations, and then eventually ILT converges to 1. Okay. So hence, the step response is, now this is the part of the response for T positive, and then for T negative, everything is 0. Initial conditions are 0, the input is 0, therefore IL T must be 0. Hence we can write that step response is, which we denote by the notation S of T. S of T for step response and H of T for the impulse response equals this thing multiplied by U of T. So let me write it once again for the sake of completeness. Plus 1, and then everything is multiplied by U of T. Next, let's consider the impulse response for the same circuit. How about impulse response? Okay. Again, we have parallel RLC topology. This is where we apply input from IS, CR, F. And this is our output of interest inductor current IL. Now again, by definition, impulse response means zero state response for the impulse excitation. Okay, so from the input you apply unit impulse function. So IST equals delta T, and the initial conditions for all dynamic components are 0. IL0 minus equals 0, and VC0 minus equals 0. Okay. Now, let's consider the previous example, or the previous parameters for the parallel RLC circuit. Okay, but before that, let's quickly remember the differential equation. Differential equation is d squared IL plus 1 1 over RC DIL plus 1 over LCIL equals 1 over LCIS. So this is the differential equation for any input. Now we consider not any input, but the impulse, okay, unit impulse. Therefore, the differential equation becomes d squared IL plus DIL plus 1 over LC IL equals 1 over LC, and then the impulse. Okay, let's consider the same circuit. Consider the same circuit parameters as in our previous example, where we took all values C, R, and L unity. R equals 1 ohm, C equals 1 F, and L equals 1 Henry. And what we're after is, we're after the impulse response, that's H of t. Note that if you already have set response, impulse response is simply its derivative, okay? Therefore, we don't have to really do any computations, but for the sake of completeness, let's obtain the impulse response by solving the differential equation. So, again, consider the case for t positive, okay, for t positive times. What we have is d squared IL plus DIL plus IL equals impulse evaluated at t positive, but by definition, when the argument is positive for impulse, it's simply 0, okay? So that means for positive times, the differential equation becomes a homogeneous differential equation, second order. And we have to figure out, of course, the initial conditions, IL0 plus and DIL 0 plus to solve this differential equation. For that, let's quickly see whether this IS, when its impulse function produces any jumps at either capacitor voltage or the inductor current. So for this, we do our, let's call this equation. So for this, let's do our 0 minus 0 plus interval analysis for t between 0 minus and 0 plus. Let's figure out whether we have any jumps for the inductor current. That is, whether IL0 plus is different than IL0 minus. Not that IL0 minus is 0. Okay. So IL0 plus is IL0 minus plus 1 over L, and then we integrate the inductor voltage. 1 over L from 0 minus to 0 plus inductor voltage, and then inductor voltage, same as the capacitor voltage. So here we can write VCT dt. And then remember that capacitor voltage, even though it can make discontinuities, can make jumps, it's always bounded. And if it's bounded, since we're integrating, and if you test with tiny interval, what it produces is 0 at the output of the integral. So this is 0, this was 0, therefore IL0 plus must equal 0. Therefore, inductor current must remain continuous, okay, in that topology. Now, how about VC 0 plus? So let's do that. Now, to figure out whether VC makes any jumps at t equals 0, we need to figure out the impulsive component of the capacitor current. Okay, so it's what we're doing is the dual of what we did here. To determine whether the inductor current makes any jump, we have to figure out the impulsive component of the inductor voltage, which in this case is the capacitor voltage. Okay, so for what we do for that is we go to our circuit, and since the impulsive component will not depend on the bounded sources, okay, for our analysis, what we do is we replace the capacitor voltage with any bounded voltage source and inductor with any bounded current source. Now, since no matter what bounded sources we choose, we will always obtain the same impulsive component for the capacitor current and the inductor voltage, we stick to the simplest possible bounded sources. Okay, so for capacitor, we choose the 0-volt bounded voltage source, which is no other than a short circuit. And then for the capacitor, we replace it with a current source that provides 0 amps. So a current source providing 0 amp means it's an open circuit. The inductor is replaced by an open circuit, and a voltage source producing 0 volts is equal to a short circuit. Okay, so we replace the capacitor with a short circuit. Okay, and then in this case, all the current will be flowing over the capacitor of this short circuit. So clearly, VL in this circuit is 0. Okay, so that's another way to see that IL0 plus must equal IL0 minus, because what we're doing is we're integrating 0 and the outcome is 0. Okay, and as for the capacitor, since all this current is flowing over the capacitor, the impulsive component of capacitor current is delta t, and that will produce a jump at the capacitor voltage. So let's figure that out. ICT equals delta t, impulse. Therefore, VC0 plus equals VC0 minus plus 1 over C, 0 minus 0 plus. And we're integrating the capacitor current. That's VC0 minus plus 1 over the capacitance, 1 over C. Therefore, VC0 plus in our case is, this is 0, C is 1 farad, therefore VC0 plus is 1 volt. And then DIL0 plus is VL0 plus over L, and VL0 plus is VC0 plus, and L is 1, so therefore VC0 plus over L. This is 1, this is also 1, so we have 1 amps per second. Okay. Now, we can return to the equation star, because at this point, we have figured out IL0 plus and the IL0 plus. So we have everything we need to write down the solution. Okay. Now we return to star. The characteristic polynomial, for characteristic polynomial, we look at the left hand side, and the of s is s squared plus s plus 1, that yields s plus 1 half squared plus 3 over 4. So we have natural frequencies minus 1 half plus minus j squared 3 over 2. So this we already obtained, you already know from the previous example. Okay, the natural frequencies, they do not depend on the input. Okay, therefore, to find natural frequencies, you can, whatever the inputs are, you can just kill them all and then deal with the homogeneous case to find it. Okay, then ILT this time, since the right hand side is 0, we will only have the homogeneous part for our complete solution. ILT is K1 e to the minus T over 2 sine square root of 3 over 2T plus K2 into the minus T over 2 cosine square root of 3 over 2T. And to find K1 and K2, we apply the initial condition constraints. So IL0 equals 0. Plugging t equals 0 here, the sign term will disappear, and what you have is K2 equals 1. Excuse me, K2 equals 0. Okay. K2 equals 0. And then, now this 0. Then you differentiate IL, and then plug in t equals 0, and the right hand side must be 1. So let's do that. DIL0 equals 1. So that implies square root of 3 over 2 K1 equals 1, which gives K1 equals 2 over square root of 3. Okay. Hence, the impulse response for the circuit is h of t equals 2 over square root of 3 into v minus t over 2 sine square root of 3 over 2 t amps. So you can check whether S of t that we obtained, the step response from the previous example, whether that equals whether the derivative of that equals h of t or not. If it doesn't, then it means we made an error statement. Okay. Now, next example, we're going to consider a circuit that can be reduced to a series RLC circuit. So this is the topology, 100 ohms, 25 millihenry. Here we have 30U minus T milliamps. This is 5 microfarads, and this is the polarity of the capacitor voltage. Question is VCT. We have to figure out VCT for T positive. For T positive. Okay. So what we do is, well, first let's look at the circuit. What happens for T positive is the argument of this step function becomes negative because inside brackets we have minus T. Okay. For all negative times, it produces constant current at 30 milliamps, and at T equals 0, it just shuts down and drops to 0. Okay, so therefore for T positive this becomes open circuit, this source. And what we have is just a series connection of this resistor, inductor and capacitor. So what we require therefore is we have to figure out the initial conditions for T equals 0, and then once we have the initial conditions we will have to solve the homogeneous series RLC circuit. Okay. So to figure out the initial conditions that we will need for our solution, let's look at the T negative case. Now we're going to make an assumption. We're going to assume that the circuit has reached steady state, okay, before time T equals 0. Assume that the circuit is at DC steady state. Okay, at for t negative. So that means every voltage and every current is constant. Okay. Okay. Now, VL, the inductor voltage, equals what? L diL. Okay, that's the term equation. By assumption, or by definition of DC steady state, means everything is constant. Therefore, inductor current is also constant. That means rate of change of inductor current is 0, and from term equation, that produces 0 volts for the inductor voltage. The dual case is true for the capacitor. Capacitor current is C dVc, okay, and everything is constant. Therefore, capacitor voltage is constant. Therefore, its rate of change is 0. Hence, the capacitor current must be 0 at DC steady state. In other words, at DC steady state, capacitor behaves like an open circuit, and inductor behaves as short circuit. Okay, and this is 30 milliamps constant, 100 ohms. Now, this is open circuit, therefore all this current will be flowing over this 100 ohm resistor and produces 3 volts. Okay. Now, since this is open circuit, IL clearly is 0, the inductor current at DC steady state, and since this is short circuit, all the voltage here across the terms of 100 ohm resistor appears also across the terms of the capacitor. Therefore, VC 0 minus, okay, just before this shuts off, VC 0 minus is 3 volts and IL 0 minus is 0. So VC 0 minus equals 3 volts and IL 0 minus is 0 amps. Now for T positive, okay, for positive times, the argument of this step becomes negative, therefore it just drops to 0, the current produced by this current source. Hence, for T positive, we can replace it by an open circuit. And the circuit becomes the following series RLC circuit. Ohms, 25 millihenry. This is IL, 5 microfarads. This is VC. Okay. Now we have derived the differential equation for the series RLC circuit in our previous lecture, and it reads R over L dVc plus 1 over LC VC. And we have no source, therefore the differential equation is homogeneous, okay, with 0 right hand side. And for the parameter values that are given, this differential equation boils down to d squared VC plus 4,000 dVc plus 8 million VC equals 0. So we have the differential equation. We need the initial conditions, namely VC 0 plus and dVc 0 plus, and we will be ready to work on the solution. Okay, so what are the initial conditions? Since we deal with T positive, we require VC 0 plus and dVc 0 plus. VC 0 plus is VC 0 minus, and that's 3 volts. It's not difficult to see that, or you can show it as an exercise. The capacitor voltage will not make any jumps, okay, in this circuit. Likewise, inductor current will not make any jumps either. Therefore, we automatically have capacitor voltage and inductor current at t equals 0 plus. So, for this differential equation, we need the initial condition of the rate of change of capacitor voltage, and dVc 0 plus is IC 0 plus over C, using the thermal equation for capacitor, and IC and IL, they are the same current. Therefore, we can write this as IL 0 plus over C, and IL 0 plus is 0. Therefore, dVc 0 plus must be 0. Okay, so we have therefore VC 0 plus and also dVc 0 plus. Then we can start writing down this one. The right-hand side is 0, therefore we will only have the homogeneous solution. For homogeneous solution, we need the natural frequencies, and natural frequencies come from the characteristic polynomial. Okay, in particular, natural frequencies are the roots of the characteristic polynomial. The characteristic polynomial is, we're told the characteristic polynomial directly by the left-hand side of the differential equation. In this case, we have s squared plus 4000 s plus 8 million as our characteristic polynomial. D of s equals s squared plus 4000 s plus 8 million, and this can be written as s plus 2000 squared plus 2000 squared. Okay, and from that we can easily pull the natural frequencies, or we can easily see the roots. The roots are at S12 minus 2000, the real part coming from here, plus minus J 2000, the imaginary part coming from here. That means capacitor voltage will have the following form: e to the minus 2000t times K1 sine 2000t plus K2 cosine 2000t. For K1 and K2, we use initial conditions. Vc 0 equals 3 and dVc 0 equals 0. Okay, Vc 0 equals 3 implies plug in t equals 0. This is 1, sine disappears, and what we have is K2. So K2 must be 3. And dVc0 equals 0 implies minus 2000 K2 plus 2000 K1 equals 0. K2 was 3 from the previous computation, therefore K1 must also be 3. Okay, now K2 and K1 computed or known. Now we have the response, okay, VCT. Therefore, capacitor voltage must be 3e to the minus 2000 t sine 2000 t plus cosine 2000 t equals 4 t positive. Okay, and how this looks like is we start at at 3 volts at t equals 0. Okay, so we're here and we're starting flat, okay, because dVc 0 equals 0. Now what we're heading toward is, although these two guys will oscillate forever, they're multiplied by e to the minus 2000t, so that means they will very rapidly converge to zero, those oscillations. So we expect something like this. Okay, everything is going to zero.